Hello everyone, my name is Joshua. Today, I will present our work titled On Manipulating Syntax in the World with Diffusion Model. Here is our outline for today. Introduction. Syntax manipulation has been implemented in real-world applications such as sans translation, where the goal is to translate the captured syntax into the desired language. Second, privacy protection, such as license plate by removing the text from the captured license plate. And the third is data augmentation for boosting syntax detection or recognition models. Background problem. Several attempts have been made to solve this issue, such as SRNet, Stefan, and DRender. While this method performed well in specific scenario, a straightforward implementation of in-the-wild data still produces poor results, as shown in this figure. One of the solutions is to utilize the diffusion model. The rise of the diffusion model has shown its potential. This method is able to beat the GAN-based method without an explicit ground truth image for training, and can generate an image from the given prompt. Among other diffusion models, the latent diffusion model, or we know as stable diffusion, is commonly used as the baseline model. Furthermore, Imagic has extended LDM to allow users to edit the image from the given prompt. Here, we notice two problems. First, a straightforward implementation of LDM to syntax proved to be unfeasible. As illustrated in the first figure, when prompted with text that read maps, the expected output image should feature syntax displaying maps. However, the resulting image portrays a map instead. Second, implementing Imagic directly for syntax is also unattainable. As we can see in the second figure, the edited scene remains unchanged compared to the input image. Here, we summarize the problem into 3 points and formulate 3 challenges we must solve. Proposed method. In this paper, we introduce diffusion-based syntax manipulation network, or we call it as DBEST. Our approach is capable of generating syntax based on a given prompt and possess the ability to manipulate the generated syntax. First, we answer the first challenge. How to make diffusion model perform well in syntax? First, for image generation, our model has no modification over the original LDM, thus allowing easy integration into other text-related pipeline. Then, we fine-tune LDM using synthesized syntax, or we call it as syntax dataset, and incorporated reconstruction loss during the training. For the manipulation process, we split our process into 2 steps. First, one-shot style adaptation. This step aims to extract the style of the input syntax, such as font type, color, geometry, and background. This step involves fine-tuning the diffusion model using reconstruction loss. Second, for editing the text, we introduce text recognition guidance. This step is designed to edit the text within the image while preserving its original style. We fine-tune the condition embedding using a text recognition loss. Experiment detail. We evaluate our method on several datasets, such as syntax, text COCO, and ICDAR2013 datasets, the common datasets used for text recognition. For the evaluation metric, we use PSNR, SSIM, and LPIPS metrics for image quality evaluation metrics. In addition, we use the Object Character Recognition metric to measure the readable text quality. We also add more additional results on ICDAR 2015, IIT5K, SVT, higher text, and YouTube video datasets. Please note that ICDAR 2015 and SVT datasets are particularly challenging due to the presence of factors that can affect captured syntax, including geometry distortion, noise effects, and motion blur. Result. In this figure, we highlight 2 drawbacks encountered by prior work. Either the text is edited but the style is altered, or the style is maintained but the text remains unchanged. Our method surpasses all prior prior works by generating realistically edited syntax while preserving its original style. Evaluation. We evaluate our method against prior works regarding image quality and OCR metrics. As we can see, our method significantly outperforms prior work with a fast gap. We also evaluate each component of our proposed method and show its contribution regarding the evaluation metric. For example, why do we need to train with syntax dataset? By and large, we observe that the Lion dataset compresses general scene. Therefore, a straightforward approach of using LDM for text-to-syntax fails. The second is the text recognition guidance. According to the table 1, when the text recognition guidance is not used, the character accuracy and the word accuracy are around 84% and 60% respectively. This is further confirmed by figure 1, where we can see that the manipulated scene text contains some character errors. However, with the addition of text recognition guidance, the diffusion model is guided to revise the character error, resulting in a significant improvement in word accuracy. In essence, the text recognition guidance helps to improve the accuracy of the edited syntax by guiding the diffusion model to revise the character errors. By incorporating this guidance, our approach is able to generate more readable and accurate edited text scene, improving the overall quality of the output. Next is the one-shot style adaptation for diffusion model is crucial for maintaining the source appearance and text geometry of the edited text. As shown in the figure 1, our approach can successfully edit the text, but the edited result loses its source appearance without one-shot method. In other words, without the one-shot diffusion model, our method may generate an image that doesn't resemble the original input. The one-shot style adaptation reduces the distribution space of the diffusion model, ensuring that the generated image maintains source appearance of the input image. Here is for more results. In conclusion, our method is the current SOTA in syntax manipulation. And the second is our method is a diffusion-based method that able to deal with syntax. And the last is our method is able to edit the syntax. For the future work, our method currently has two limitations. First, the inference time is around 8 minutes per image, making it unsuitable for real-world or real-time application. Second, there is a constraint on the character length that can be manipulated. As we mentioned in the main paper, adjusting the font size is another challenge we aim to address in this future work. So I think that's all. Thank you for listening.